I wrote this is the example we just did in the class, and this is an example we proved in class actually that limits exist. And what we are doing here is not proving in a different ways to kind of relate this fact to the level curves. So that was the function, and this is the level curve. Let me show you the level. So as I increase this index, the actual level is this one, so 0.33. So these are the collection of all the points where the f value is 0.33. So in particular, if you remain in here, and because this curve is not quite away from that point 0, there's no way you can approach 0, remaining in this 0.33. And if this path actually can arbitrarily close to this 0, that would violate the fact that we proved that this will be always approaching 0, and if that portion of the graph is close to 0, then there will be a sequence along that path that goes in here where the function value remains 0.33. So that forces the existence of a sequence whose function value approaches 0.33. That contradicts our finding here. So it verifies that this level is not going through the 0, So if I even make it closer, so if the level is 0.009, still this curve, where this is a collection of all the points where the function value is 0.09, it is not close to this origin. So you cannot approach 0, remaining in 0.09. So that kind of verifies our finding, our proof that this approaches 0. This is not supposed to get close to 0, This is the very first example, and we revisited and in class today again about this an example where it does not converge. So there is two paths, so that it goes to different values. So let's look at this in terms of level curves, excuse me. So this is level as indicated here, and this is a collection of all points with level 1. So if you plug in any of those points in here, the function value will be this value 1 here. So that shows you there's a path. If you hop along this path and using some sort of sequence, you can get close to this point 0, So if you hop along on this circle, then you get close to 0, and then function value remains 1. So along that sequence, the function value approaches 1. But if you look at different levels, so that this is level 2, it's slightly bigger, smaller than that. Level 2, if you hop along this smaller circle, and you approach 0, and then function value here remains 2. So along this second sequence, the function value in particular approaches 2. So that exhibits the two different sequences along the different circle. They both approach 0, but the function value behaves completely different. One goes to 1, the other goes to 2. So this will be a demonstration of the behavior of the level curves of the cases where the expression, the limit exists and limit does not exist. But this is not the way we prove it, but this is a good demonstration using these level curves. Another thing I wrote here, this is going to be the set 2 question sooner or later. If we have the fact that a limit exists or a limit does not exist, and then this is the behavior of the level curves. But I'd like to ask kind of the converse question. Suppose we do not know the answer to the limit exists or it does not exist, and then I want to look at it. Okay, suppose we looked at all the level curves with the non-zero levels, and it turns out all the levels of these non-zero levels away from 0, Does that mean this limit exists and it becomes a 0 because we looked at the 0 thing? So it's very likely, but it's a question thrown to you right now. That's going to be set 2 problems sooner or later.